Hello everyone. On this video we will be taking a look at related rates. So basically these are, I guess you could say, story problems where finding the derivative using the chain rule comes in very handy. Alright, so let's say, to kind of give you an idea of what we'll be doing, let's say, for example, we know that the volume of a cone is equal to pi over 3 times the radius squared times the height. Okay, so to help you visualize it a little bit, let's say we have our cone. Okay, so we have a cone here, and let's say that cone is filled up with some liquid. Okay, it could be water, could be anything. Okay, so it's filled up. Okay, now the top part of this circle here, all the way to the edge, that circle there, of course, from the middle on out would be your radius. And from the top to the bottom, that's your height. Okay, now let's say that water is slowly dripping out. Okay, so that means your cone, which would look the same, well, excuse me if it's a little bit smaller, but you'll get the same general idea. Let's say it's dripped out over a while and your water only goes up to here. Okay, so you can go ahead and just kind of fill that in a little bit. Okay, now if you notice, as time goes by, your radius changes. So it goes from being that big to now being this big. Same thing with your height. Your height went from being that tall to being that tall. Okay, so let's say it's dripping out a little bit more. Let's say over time it's dripping out to be about down there. Okay, so now your radius and your height have changed even more. Okay, so the volume of the liquid in the cone is related to the height and the radius. Alright. Now, let's say if we wanted to find the rate that the volume is changing. Okay, so the rate of change of the volume with respect to time. Alright, so now what we're going to do is find the derivative of the volume formula with respect to time. So what that would be is, that would be, well, we're going to factor out the pi over 3, just put that out front since it's a constant, times the derivative with respect to time of the radius squared and the height. Okay, so this way all we have to do is, of course, using the chain rule, is to find that derivative, which won't be too bad. Okay, so let's look at that really quick. Oh, broke my pencil, there we go. Okay, so that's going to equal, and of course here we'd have to use the product rule. Okay, so let me bring that down a little bit so it's not all jammed up there. So that's going to be pi over 3. You have the first times the derivative of the second. So you have r squared times the derivative with respect to time of h plus the second, your height, times the derivative with respect to time of your radius squared. Alright. Now if we go ahead and simplify those, gives us pi over 3, pi over 3 times r squared. And the derivative of the height with respect to time, we'll just make that dh dt, derivative of height with respect to time. Plus, you have your height times the derivative of your radius squared with respect to time. This is where your chain rule will come in handy, because you're going to take the derivative of the whole thing, so that's 2r times the derivative of what's inside, dr dt. Alright, so that lets us know that our rate of change of the volume with respect to time would equal pi over 3 times r squared times the derivative of the height with respect to time plus 2 times r times h times the change in the radius with respect to time. Okay, now this is the change in volume with respect to time formula for this particular volume. It changes if you're looking for the volume of a rectangle or you're looking for the area of a square. It changes, the formula changes. Okay, so this is just an example of how you would find it. Alright, so if you're still writing, feel free to press pause, but we're going to go ahead and move on to our first example. Alright, so let's say, for example, suppose x and y are both differentiable functions of t, and are related by the equation y equals x squared plus 3. Okay, so we want to find dy dt when x is equal to 1, given that your dx dt is equal to 2. Let me kind of focus that a little bit. There we go. All right. So to solve this one, we're going to look at what's given to us first. Okay, it's given that x is equal to 1 and your dx dt is equal to 2. And we want to find our dy dt. All right, so if we just go ahead and write our formula, let's say y equals x squared plus 3, you want to find the derivative with respect to t. So of course we have to find the derivative of both sides. So you have the derivative with respect to t of y equals the derivative with respect to t of x squared plus the derivative with respect to t of 3. Alright, so this would just give us our dy dt. You have dy dt is equal to the derivative of x with respect to t. Again, we use the chain rule because it's with respect to t. Okay, so we take the derivative of the whole thing, so that's 2x times the derivative of what's inside of the x. Now, if that was with respect to x, then it would just be the 2x. But since it's with respect to t, we do the 2x and then multiply it by the derivative of x with respect to t. Plus the derivative of a constant, no matter what the variable is 0. So that actually, we could have crossed that out from the beginning if we wanted to. Okay, so we know that our dy dt is equal to 2x times dx dt. All right, but we know that our x is equal to 1, and our dx dt is equal to 2. So that means our dy dt is equal to 2 times 1 times 2, which is 4. Okay, so we're going to be pretty much using this same technique on the remaining examples, the story problem examples. This is just kind of introduce you to how it's going to go. And we're just using the chain rule that we've gone over already. All right, so if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. Okay, so let's say for this example, a spherical balloon. Oh, let me start off with the better description of it. Let's say air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Okay, and just to kind of clear it up how we're going to use it later, 4.5 is the same as saying 9/2. So you can use either one. Okay, so let's say you want to find the rate of change of the radius when the radius is 2 feet. All right, so the first thing we notice is that it's a spherical balloon. Okay, so when we see spherical balloon, we know we want to use that volume is equal to 4/3 times pi radius to the 3rd power, because that's the volume of a sphere. Okay, so somewhere in the problem, they usually tell you what formula you're going to go with. Okay, move that up a little. So we're given that the volume is changing at a rate of 4.5 cubic feet per minute. So the rate of change of the volume with respect to time is equal 4.5 cubic feet per minute. Okay, what else do we know? We know that we're looking for the radius when the radius is 2 feet. Okay, so we know when the radius equals 2 feet. So we can kind of put a little square around that. Okay, so now what we're going to do is derivative of volume with respect to time. Remember, this is our volume of a sphere. And we're just going to factor out the 4/3 pi since that's a constant. And we know that's the derivative with respect to time of the radius cubed. Okay, so that means the derivative of the volume with respect to time is going to equal 4/3 pi. So that will be 3r. The derivative of r to the third power with respect to time is 3r squared times the derivative of r with respect to time. Again, using our chain rule. Okay. So you can see here those 3's cancel each other out. So the rate of change of the volume with respect to time is equal to 4 pi r squared times your dr dt. Okay, which means this is the rate of change of your radius. Just this part. Okay, this part here is the rate of change of your volume with respect to time. This is the rate of change of your radius with respect to time. Okay, so now that you've found the derivative, you plug in your givens. Okay, so we know that derivative of the volume with respect to time is 4.5 or 9/2. So you have 9/2 equals 4 pi times your radius squared. Remember, your radius is equal to 2. Move that up some. So your radius is equal to 2, so that would be 2 squared times your rate of change of your radius with respect to time. So that's dr dt. Okay, remember, they want us to find the rate of change of the radius. So that means we solve for our dr dt. Okay, so you have 4 times 2 squared, so 4 times 4 is 16 pi. So we divide both sides by 16 pi. Okay, so these two will actually cancel each other out. So that means your change of the rate with respect to time is equal to 9/32 pi. Which, if you plug that into a calculator, gives you approximately 0.0895 feet per minute. Alright, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to another example. Okay, so let's say for this example, let's say we have a square that has a side length that is increasing at a rate of 19 inches per minute. What is the rate of change of the area? What is the rate of change of the area when the side length is 5 inches? So again, they tell you everything you need to solve this. Okay, so first you have to look at the fact that it's a square. Okay, when you have a square, all four sides are of equal length. Okay, so let's say you have a square. That means if this side is length S, I'll put a little line through the S so it doesn't look like my 5 if I start writing fast. Okay, so you know for a square, all sides are equal. Okay, so we know that the area of a square is equal to length times width, which is S times S. So it's S squared. Okay, so what do we have to do? We have to find the rate of change of the area. Okay, so we have to find the rate of change of the area with respect to time. Okay, so how do we do that? Well, we have our area. So rate of change of the area with respect to time is equal to the derivative with respect to time of S squared. Okay, so solving that, our dA dt is equal to, remember the derivative of the S, times ds dt. Let me derivative of S squared with respect to t give us our 2s times the derivative of what's inside. Alright, so now that we have our formula, we look at what's given to us and plug those in. So we see given, we know that the rate of change of the side with respect to time, remember the side length is increasing by 19 inches. So that's 19 inches per minute. Inches per minute. And what else do we know? We know that our side is equal to 5 inches when we want to know the rate of change of the area. So we just go ahead and plug those in. So derivative of the area with respect to time is equal to 2 times your S, which is 5, times your ds dt, which is 19. Okay. So we know that the rate of change of the area with respect to time is equal to 190 inches per minute. Okay. So if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. Okay, so let's say if we have a box that has a width of 12 centimeters and a length of 9 centimeters. Okay, so the volume of the box is decreasing at a rate of 541 cubic centimeters per second. Okay, well, put a comma there. With the width and length being held constant. Okay, so we want to know what is the rate of change of the height in centimeters per second when the height is 6 centimeters. All right. So we start off with looking at this and finding out what are we looking for. Okay. Well, it's saying the box with a width and a length of that, and we're looking for the volume of the box since it's decreasing. Okay, so using the volume of a box, remember that's your length times your width times your height. Okay, so what are we looking for? We want to know what is the rate of change of the height. Okay, so we want to find the rate of change of the height with respect to time. Okay, so the first thing we do is we see what's given to us. Okay, so they already told us our width is 12 centimeters. And our length is 9 centimeters. Okay. They also told us that the volume of the box is decreasing at a rate of 541 cubic centimeters per second. Okay, so when we saw that volume is decreasing, we know that the rate of the volume with respect to time is not just 541, but it's a negative 541. Because when it's decreasing, it's going to be negative. Okay, now if it was increasing, it would stay positive. But since your volume is decreasing, it's going to be a negative there. All right. Now, what else do we know? We know that the length and width are constant. Okay, so we know these 4 things. Okay, so now if we get our volume, we have to find the rate of change of the volume with respect to time. So rate of change of the volume with respect to time is equal to, now this is kind of the part where it's easy to miss. When they tell you that the length and width are constants, we treat those as constants. So we treat that as if it were a 7 and an 8. We can factor those right out. So since those are constants, so your length and width, those are constants. I'll move that up a little. Okay, so now we just have to find the rate of change with respect to time of the height. Okay, so really that gives us our dv dt is equal to your length times width times your dh dt. All right, and all 3 of those we know because they are our givens. Okay, your volume is decreasing, so that's negative 541. equals, your length is 9 and your width is 12. So you have 9 times 12 times your dH dt. Okay, so if we go ahead and multiply those two, we have negative 541 is equal to 108 times the dH dt. Alright, so if we go ahead and divide both sides by 108, our rate of change of the height with respect to time in centimeters per second is negative 541 over 108. And you could plug it in for a decimal number if you like, but you don't have to. It all depends on what the particular problem asks for. Now, if they would have asked, set the problem as 2 decimal places, then you plug it into a calculator and get a decimal, but you don't really have to here. Alright, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. Alright, so let's say, for example, a triangle has a base that is decreasing at a rate of 19 millimeters per minute and a height that is constant. Okay, so what is the rate of change of the area of the triangle when the height is equal to 4 millimeters? Okay, so what I want you to do is I want you to press pause, but I'll give you a little hint of how to get started on this one. Okay, so hint, the area of a triangle is equal to 1/2 the base times the height. Okay, so I want you to press pause and try to work this one out on your own. Alright, so I'm assuming you've pressed pause and you've worked this one out on your own. Let's go ahead and verify your answer. Okay, so we know that the area of a triangle is 1/2 base times height. Okay, now when they see the rate of change of the area, rate of change of the area that's the rate of change of the area with respect to time. So that's going to equal 1/2 times the derivative with respect to time of your B and H. Okay, so we have 2 variables, which means we have to use the product rule. to find the derivative of those. Alright, so I'm going to move this over to the left a little bit. Move that up. Okay, so the derivative of the area with respect to time is equal to, at 1/2 times, you have the first times the derivative of the second plus second times the derivative of the first. So we have the first times the derivative of h with respect to time plus the second times the derivative of your base with respect to time, or rate of change of your base with respect to time. Alright, now if you think to what's given, they tell you that the height is constant. Okay, so we don't have to know what the height is to know that it's constant. Well, we know here it's 4 millimeters. But if the height is constant, that means it's not getting any taller, it's not getting any shorter, it's constant. So the rate of change is going to be 0 because there is no change. The height is constant. So that means the rate of change of the height with respect to time is equal to 0. Okay. Now we're looking for when the height is equal to 4, so your height is actually going to be equal to 4. And we know that the base is decreasing, so the rate of change of the base with respect to time, since it's decreasing, is going to be negative 19. Okay. Now, since your rate of change of the height with respect to t is 0, 0 times anything is just going to be 0, so you can cross that out. So you can simplify your formula a little bit. So your dA dt is equal to 1/2 times height times your rate of change of the base with respect to time. So if we go ahead and plug those in, so rate of change of the area with respect to time is going to equal 1/2 times your height, which is 4, times your rate of change of the base with respect to time, which is negative 19. So plug that all into a calculator, or if you want to just calculate it on your own. Your rate of change of the area with respect to time is equal to negative 38 millimeters per minute. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. Okay, so let's say, for example, the volume of a sphere is increasing at a rate of 555 cubic millimeters per hour. What is the rate of change in millimeters, well, millimeters per hour, that part would help, in millimeters per hour of the radius when the radius is 5 millimeters. And you want an exact answer. which means you don't want to have to worry about decimals or anything like that. All right, so what I want you to do is, again, I want you to press pause and try to solve this one. Well, let me give you a hint first. The volume of a sphere is equal to 4 over 3 pi radius cubed. Just to kind of give you some place to start. Okay, so go ahead and press pause, and I want you to solve this one, or try solving this one on your own. All right, so I'm assuming you've pressed pause, you've worked this one out on your own, and let's go ahead and verify your answer. All right, so first thing you notice is that your volume of a sphere is 4 over 3 times pi radius to the third. So we want to know the rate of change of the volume. So the rate of change of the volume with respect to time, we get that 4 over 3 pi, and we factor that out. So 4 over 3 pi times the derivative with respect to time of your radius cubed. Okay, so that means your rate of change of the volume with respect to time is 4 over 3 pi, derivative with respect to t of r to the third, that would give us 3r squared times your dr dt. Okay, so if we go ahead and simplify that, because those two 3's cancel each other out, your rate of change of the volume with respect to time is going to be 4 pi times your radius squared times your dr dt. All right, so now we look at our givens, or maybe you looked at your givens before you did this. Either way, it doesn't matter as long as you have them figured out. So here, volume is increasing at a rate of 555. So rate of change of the volume with respect to time is going to be positive 555. And we're looking for when our radius is equal to 5. Okay. Now, since we're looking for the rate of change of the radius, we're basically solving for this right here, the rate of change of the radius with respect to time, which means we're going to replace our r and our dv dt. So we have everything we need. Okay. So rate of change of the volume with respect to time is 555 is equal 4 pi times 5 squared times dr dt. Okay, so you have 5 squared, which is 25 times 4, so you have a 100 pi. So 555 equals 100 pi times dr dt. Okay, so we're going to go ahead and divide both sides by 100 pi. Bringing that up a little bit. So 555 divided by 100 pi. Well, I can switch that around. You don't have to, but I just like to have my dr dt on the left. Equals 555 over 100 pi. Okay, so that's going to equal 111 over 20 pi once you simplify it, since both of those are divisible by 5. And they want the exact answer, so you're going to leave it like that. So it's millimeter per hour. Okay, so of course I can't give you an example of every problem you will ever see, But this gives you, hopefully, a procedure, a process, a way to approach each problem. Okay, so hopefully this video made sense, and I will see you on the next video.